It is 3 in the morning and your phone is buzzing. The load balancer in front of your production fleet has stopped passing traffic. Not the application. The load balancer itself. You are now awake in a terminal trying to work out whether the process died, whether the certificate expired, whether the machine ran out of file descriptors, or whether the whole availability zone it lived in has gone away. This is the scenario that managed load balancers exist to delete from your life. In this video, we are going to work out exactly what a managed load balancer is, what the cloud provider takes responsibility for, and what remains yours. How the major offerings from Amazon, Microsoft, and Google actually differ, and the two real trade-offs that make teams walk away from managed services. By the end, you should be able to argue either side of this decision with specifics rather than vibes. To appreciate what you are buying, start with what you would otherwise build. Self-managing a load balancer means you provision virtual machines, install something like Nginx or hproxy on them, write and version the configuration, install and rotate TLS certificates, and keep the operating system patched. That is the easy part. The hard part is everything that keeps it alive. You now need at least 2 load balancer instances, because one is a single point of failure. You need those instances in different availability zones. You need a mechanism to fail traffic over between them, which usually means a floating IP address or a health-checked DNS layer. And you need monitoring on the load balancers themselves, because the thing watching your servers now needs something watching it. So you have accidentally built a distributed system whose only job is to point at your actual distributed system. It is genuinely useful work, and for some organizations it is the right work. But for most teams it is undifferentiated effort. Your users do not pay you for a beautifully patched proxy tier. A managed load balancer inverts that. The cloud provider already operates a large, hardened, multi-tenant load balancing fleet. You do not get a virtual machine. You get an endpoint and an API. You declare what you want, usually through Terraform or the console, and the provider's control plane makes it so. There is no host for you to log into, and that is the entire point. Concretely, 4 things move from your side of the line to theirs. High availability across zones. Automatic scaling of load balancer capacity as your traffic grows. Health checking of your backends. And automatic failover when a backend or an entire zone disappears. Notice that all 4 are the operational burdens, not the routing logic. The routing logic is still yours to design. Before we compare providers, you need one concept, because every provider's product line is organized around it. Load balancers operate at one of 2 layers. A Layer 4 load balancer works with TCP and UDP. It sees addresses and ports. It does not open the payload. It does not know what HTTP is, and it therefore cannot make decisions based on a URL. A Layer 7 load balancer terminates the connection and actually parses HTTP. It can read the path, the host header, the method, and the cookies. That unlocks routing by URLs sending /API to one target group and /images to another. It can also terminate TLS, insert headers, and rewrite paths. All of that costs a little latency and a lot of capability. Here is the practical rule. If you are serving HTTP and you want to route by anything inside the request, you need Layer 7. If you are balancing raw TCP, or you need the absolute lowest latency, or you must preserve the client's real IP address at the network level, you want Layer 4. Almost every provider sells you one of each, which is why their product lists look confusing at first glance. Start with Amazon. AWS gives you the application load balancer, which is the Layer 7 product. It routes on host and path, it supports HTTP2 and WebSockets, it integrates with AWS Certificate Manager for TLS, and it can send traffic to instances, IP addresses, or Lambda functions. For most web applications on AWS, this is the default answer. Alongside it sits the Network Load Balancer, the Layer 4 product. It handles millions of requests per second at very low latency. It can hand you a static IP per availability zone, and it preserves the client's source address. You reach for it when you are balancing raw TCP or UDP, when you need extreme throughput, or when a firewall rule somewhere demands a fixed address. Microsoft splits it the same way with different names. Azure Load Balancer is the Layer 4 product. operating on TCP and UDP inside a virtual network, and it is the one you place in front of virtual machine scale sets. Application Gateway is the Layer 7 product, doing path-based routing, TLS termination, and session affinity, with a web application firewall available as an integrated tier. Google's Cloud Load Balancing is architecturally the most distinctive of the three. Its external HTTP load balancer is genuinely global rather than regional. You get one Anycast IP address advertised from edge locations worldwide, and a user's request enters Google's network at the nearest edge and then travels to the closest healthy backend over Google's own backbone. It also offers regional Layer 4 balancers for internal traffic. That global model is worth pausing on. With a regional load balancer, serving users in two continents means two load balancers and a DNS-based geo-routing layer on top, and failover between them takes as long as your DNS time to live. With a global Anycast address, the failover happens inside the provider's network in seconds and the client never sees a different address. Now the mechanism that makes any of this actually reliable. A health check is a request the load balancer sends to each backend on a fixed interval, entirely separate from user traffic. You define the path, the interval, the timeout, and how many consecutive results flip a decision. Typically, a backend must fail 2 or 3 checks in a row before it is removed and pass 2 in a row before it comes back. The thresholds matter more than people expect. Check too rarely and you keep sending users to a dead server for a long time. Check too aggressively and one slow garbage collection pause ejects a perfectly good backend, which shifts its load onto the others, which makes them slower, which ejects them too. That cascade is a real outage pattern and it is caused entirely by your own configuration. There is also a distinction worth knowing. A shallow health check just confirms the process is listening and returns 200. A deep health check confirms the backend can actually reach its database and its cache. Deep checks catch more real failures, but if every backend shares one database and that database wobbles, a deep check will eject your entire fleet at once. Most mature teams run shallow checks for the load balancer and deep checks for alerting. Let us trace a real failure. You have 3 backends across 2 zones. A hardware fault takes out the machine hosting backend too. Within a few check intervals, the load balancer marks it unhealthy and stops sending it traffic. The remaining backends absorb the load. Your auto-scaling group notices the shortfall and launches a replacement, which passes its checks and joins the pool. Nobody was paged. Now escalate it. An entire availability zone goes offline. Because the managed load balancer itself runs across zones, it survives, and it simply stops routing to any backend in the failed zone. This is the specific scenario that is genuinely painful to build yourself, because your own load balancer instances would have been in those zones too. Do not confuse managed with automatic. Several things remain squarely yours, and misconfiguring them is the most common cause of a managed load balancer behaving badly. You choose the routing rules. You define what healthy means. You set the idle timeout, and if it is shorter than your slowest legitimate request, the load balancer will cut that request off and your users will see mysterious 504 errors. Connection draining deserves a specific mention. When you deregister a backend during a deploy, requests may already be in flight on it. Draining tells the load balancer to stop sending new requests but to let existing ones finish for a configured period. Set it to 0 and every deploy severs live connections. Set it far too high and your deploys crawl. This is a knob people forget exists until it bites them. Now the others part because managed is not free either sense. The first trade-off is cost. Managed load balancers bill on a combination of hours and traffic processed. At small and medium scale, this is trivially cheap. At very high or very spiky volume, the traffic component can grow past what a pair of well-tuned NG-INX instances on raw virtual machines would cost you. But be careful with that comparison, because the self-hosted column is almost always understated. It has to include the engineer hours to build it, the ongoing hours to patch and upgrade it, the cost of the standby capacity you keep for failover, and the expected cost of the outage you will eventually have. Teams that switch to self-hosted purely on the invoice number frequently regret it. The second trade-off is customization. You get exactly the knobs the provider exposes. If you need a custom Luam module, an unusual protocol, a bespoke rate limiting algorithm, or header manipulation the product does not support, you are stuck. You cannot patch someone else's data plane. This is the constraint that most often genuinely forces teams to self-host. There is a third consideration people raise, which is lock-in. It is real but usually overstated for load balancers specifically. The configuration is provider-specific, yes, but the concept is universal and the surface area is small. Migrating a load balancer between clouds is a genuinely bounded piece of work compared to migrating a managed database or a proprietary queue. So here's the decision rule. Start managed. Always. Then self-host only when you can point at a concrete, specific reason. A routing requirement the managed product cannot express. A cost curve that has actually measurably flipped at your scale, or a latency budget the managed product has been measured and shown not to meet. Notice all three are measurements, not opinions. One more nuance. It is not strictly binary. A very common production shape is a managed load balancer at the edge, terminating TLS and handling zone failover, forwarding into a self-managed proxy layer like Envoy or an Ingress controller inside your cluster, which does the sophisticated routing. You get the provider's availability at the front and your own flexibility behind it. Let us convert this into interview answers. First question. Why would you use a managed load balancer instead of running NGINX yourself? The answer is that you are outsourcing availability, capacity scaling, health checking, and failover of the load balancing tier, so you do not have to build a redundant proxy fleet with its own failover mechanism and its own on-call rotation. Second question. When would you not use one? Answer with the three measurable reasons. A routing requirement the managed product cannot express. A cost curve you have actually computed and found to cross. Or a latency budget you have actually measured and found it fails. Saying it is cheaper without a number is exactly the answer that gets probed. Third question, and this one separates people. What is the difference between the application load balancer and the network load balancer? Answer. ALB is layer 7. It parses HTTP and routes on host and path. And LB is layer 4. It forwards TCP and UDP, gives you a static IP, preserves the client address, and adds less latency. Choose by whether you need to see inside the request. A fourth one that comes up surprisingly often. Your managed load balancer is returning 504 gateway timeout, but your backends look healthy. What is happening? The usual answer is that the load balancer's idle or request timeout is shorter than your backend's genuine processing time, so the load balancer gives up while the backend is still working perfectly happily. Bringing it together. A managed load balancer is the provider operating the load balancing tier for you. They own availability, scaling, health checking, and failover. You own routing rules, health definitions, timeouts, and the bill. Every provider splits the offering into a layer 4 product and a layer 7 product, and Google additionally offers a genuinely global Anycast front end. And the sentence to remember. Use the managed service until you have a measurement that says you cannot. Not a feeling that it is expensive, not a preference for control, but an actual number or an actual requirement the product cannot express. Until then, let the provider be the one who wakes up at 3 in the morning.